Okay, everyone. So let's start. So today we talk about a very important kind of force, the universal what? Okay, just so you know, everyone, technically, just so you know, even though, does anyone not have a sheet? Sorry, everyone has a sheet? We're good? Okay. Even though this is called the universal what? Gravitation, it is not the same as the what? As the fundamental gravitational force. Just so you know. This is actually the universal gravitational force as proposed by Newton back in the 1600s. Obviously, in the 1600s, they did not know anything about what? About the gravitational force, about this electromagnetic, about the strong nuclear. They did not even know really what the structure of the atom was. So this is basically what the classical way, the classical old way of what understanding gravitation between any two objects, not the new quantum way. The new quantum way is obviously much more advanced and much more elaborate. This is the old classical way proposed by Isaac Newton. Okay, so what is the actual? What's also another name for it? Well, very fittingly, I guess it's called Newton's law of universal gravitation. Go ahead, write it down. So the other name for it is Newton's law of universal gravitation. He was the first one to study it and to come up with the equation that we will follow for the next 3 days, today and Thursday and Friday. Okay, Newton's law of universal gravitation. Okay, all right. What does it? So what's the symbol for the what? What's the symbol for this force? Obviously, all forces have to have what for the symbol? F, capital F. However, is this gravitation or gravity? Which one are we talking about? We're talking about gravitation. What was the symbol for gravity? For the force of, sorry, not for gravity, for the force of gravity. F with what kind of G? Small g. So today we deal with what? Today we deal with uppercase G. Again, they are not the same. F small g is the force of what? Gravity. F capital G is the force of what? Gravitation. And you will see that the difference actually is very important. Yes? Okay. Okay, everyone, who remembers? Listen up. Who remembers what was the difference between gravitational force and gravity? Yasmin is asking. Baha. So specific to objects or any? Okay, nice. So gravitation, they have what? They have mass, each one, and they have what? Obviously, distance between them. But it could be absolutely what? Any what? Any two objects, whether it's very light or very heavy. How about gravity? Yeah. Supermassive object, that's number one. Smaller object, that's number two. Thank you. So basically, how close by is close by? As long as 9.8 meters per second squared applies, you are what? You are close by. Make sense? So a question for you. Astronauts in space right now in the International Space Station, are they under gravity or gravitation? Of course. Why can they not be under gravity? Because obviously if they drop something in the space station, does it fall down at 9.8? No way. Which means what? It's not the small g, it's the uppercase G, which we do today. Make sense? Okay. All right. So what's the symbol? F capital G. Am I missing something there? Do I need to? What did we always say about gravitation? Is it ever repulsive or always attractive? All, which means what? It always pulls things what? Out or in? Inward. Which means really, I am never gonna bother asking you for the what? The direction. I'm always gonna ask you for the what? Magnitude. Thank you. If you put it, absolutely no problem, 100%. But I'm never gonna bother asking you for what? For the direction of the gravitational force. We all know it pulls things closer. So I'm just gonna ask you how much force is on them. Okay? All right. What is it? It's the mathematical law. It's a formula already made in the 1600s by Isaac Newton that determines how much force of attraction, of course, is between two objects, as Yasmin said, that have masses and have some non-zero distance between each other. All I'm saying about non-zero distance that obviously if two objects have zero distance between each other, they are not two objects, they are now one single object together. Okay, so it has to be both objects are distinct. Okay, so it relates four physical quantities. What does it relate? Well, one of them is the mass of object one, of course. One of them is mass of object one, whichever one you want to define as object one. The one on the right, the one on the left, the one on top, the one at the bottom, whatever. Obviously, the second one is what? Mass of object two. Okay, so that's two factors so far that matter to the equation. What's the factor number three? Obviously, yes, the further they are, the weaker the physical attraction between both of them. Thank you. So the distance between And this is, everyone, this is a very huge issue here. The distance in this formula has to be taken between the what? Centers of objects. Gravitation needs you to actually go from center of object to the center of the other object, not from surface to surface. You will see if you do not account for the center to center, your value will be completely two things, different and completely wrong. Okay, we'll see that. And what's the fourth thing? The thing that we usually are interested in. What is the amount of force of gravitational attraction between the two objects? Okay, so these are the four players in this equation. Obviously, I can give you how many? Three, and I have to ask you four. You always have to identify three of them, and the fourth one will be the one that you need to find. And depending on that, sometimes it becomes an easy one, like what? Plug and play, like some of the kinematics, or what? A rearrangement, cross multiply, whatever it needs to be done. Okay? All right. So this is the first slide that identifies what the FG is and what are the main players in the whole thing. Okay? All right. So let's actually talk about the equation. Okay? What is the equation of F capital G as proposed about 450 years ago? Okay? All right. Everyone, here is the equation. Okay? Gravitational force. I think I have enough space for you to write. Yes. So the first space is for you to write it as a word equation. So the gravitational force is equal to a very important something called the gravitational what? Constant. Yes, gravitational constant. This is, by the way, how much of a constant is this? It is a physical constant. It's as much of a constant in physics as much as pi is a constant in math for circles. Same thing, never changes. Gravitational constant. Now, very important. What happens at the top? Mass of object one. Everyone, what's this sign? Multiply. Okay, I don't know for whatever reason, but I swear, every single course I teach, when people start to apply this equation, for some whatever reason, instead of multiply, they put plus. Even though the equation is right in front of them. And yet, instead of multiplying the masses, they just do what? They add them up. Okay, they plus them up. Okay, please never do that. Now, what is the bottom part? What's the bottom part? Distance, but it's what? Center to center. Even in the word equation, I am emphasizing, please do not forget to go from center to center. And don't forget to what? To the distance. Yes, a big mistake is people forget to square. By the way, when I mark your written work, it's very easy for me often to actually know, even without doing the math, to know exactly what kind of mistake you did. Okay, because every single mistake will lead to a certain error in the solution. Okay, if you forget to square, it will. I can see. I can just look at the final answer and say, they forgot to square. If you forgot to what? If you forgot to go center center, I can tell. If you added instead of multiplying, I can tell as well. Okay, so these three mistakes are the most common ones: forgetting to multiply and adding instead, forgetting to square, and finally what? Forgetting to take the what? Center to center. Yes, thank you. You can take surface to surface or a surface to one of the centers, but you are not taking center to the center. Okay, what is this in mathematical form? There it is. F capital G, with a small g, of course, because it's a subscript, equals a capital G here, which is known as the gravitational constant. And then M1. Oh, by the way, something that I think Baha mentioned a couple of days ago is that can you use capital M for masses? Of course you can. Of course you can. It's just a symbol. It's a placeholder. However, most common in almost any math or physics textbook, the symbol for mass is always what? A lowercase, okay? Unless you have what? A big mass and a small mass. Instead of calling one of them M1 and M2, you can call one of them what? Small m, and one of them what? Capital M. Yes, yes. Oh, okay, okay. Oh, how do people know the 6.6? Did you look it up, or you just know it? Okay, all right. I like that. In my course, people sometimes are watching the video before class starts. That's fine. Yes. Tell me something about this number. Is it a big number or a small number? Why? What in that number tells you it has a very, very small magnitude? Exactly. The what? The negative 11 power. Can you remind me again what was one of the most important properties of the gravitational force? It was the what of all four forces? It was the what? It was the weakest. Why do you think it's the weakest? Because that very small constant is already built into the what? It's already built into the what? The formula and the equation. You got it. This is actually the mathematical reason why the gravitational force is the weakest. Every time you plug it in, you have to multiply that fraction by how much? 6.67 times what? 10. By the way, how do you write this in standard notation? How many zeros do you need before the 667? 10, exactly. Imagine 0.10 zeros and then 667. That will make any number go what? Go down very, very, very much. There you go. Okay? Okay. Yasmin is asking, so what is that 9.8? Okay, I want you to know very, very carefully. 9.8 has to do with what planet only? Earth. And where again? On the what? On the surface of the Earth. What is this? This is called the what? The gravitational constant in the entire what? In the entire, do you see what I mean? The 9.8 is only what happens to a what? To an object, to an object, if you drop it where? Close to the what? To the surface of what planet? Earth. Do you think 9.8 also applies on the moon? No way. We're going to actually learn on Friday how to calculate what the G of absolutely any spherical planet. What's up? Oh, it's actually super accurate. This one, okay, you're still confusing the big G with the what? With the small g. They actually have nothing to do with each other. That G, by the way, 9.8 is measured in what? What's the meters per second? So it's really a value of what? Acceleration. This has nothing to do with acceleration. This has to do with what? Do you see what I mean? They are just the same letter, but they have nothing to do with each other. Is that making sense now? The other G is the acceleration of a falling object. Sorry, not a falling, a free fall object on Earth. This one is the universal gravitational constant between any two objects in the what? In the universe. Thank you. Yes. No, absolutely. If it were zero, what does that mean? Nothing would be holding you down, which means you can't land anything, you can't walk on it, you can't send a rover to it. Not, it would float as much as what? As much as what? As much as the space station. In space station, are you going like falling down or just floating everywhere? Exactly, because there's no gravity on you. Well, there is gravity on you, but it's very, very what? Insanely small. Okay. That's the point of today, tomorrow, sorry, Thursday and Friday, and then you will actually be able to make a distinction. That's the whole idea. Yes, gravity. You have to be not tethered. You have to be what? On a planet or super close to it. Gravitation, you could be anywhere, including what? On a planet. But it's a special case. Okay? You hold on. Yes. Hold on. All right. Yes. Yes, if you are actually in a what? In a very, very, very deep patch of space with absolutely what? Nothing around you for what? Light years. Do you see what I mean? Think about it. Gravitational force is already what? Strong or weak? So that means what? Okay, question for you. Okay, how far is the International Space Station above the surface of the Earth? Is it like millions of miles? No. It's like what? 700 kilometers, right? It took just that much to what? To almost eliminate the what? The gravity of the Earth. Do you see what I mean? So that means if you're really, really super far from any planet or any star, you're probably gonna feel what? Absolute. Do you see what I mean? And this is my I like to call this my theoretical lab. We take things there to what? Eliminate friction, eliminate gravity, eliminate everything, and just purely what? Deal with what? Newton's first law or second law and third law and so on. Okay? All right. So small. Okay. Question for you. Everyone, what is the standard unit for mass? What did we say yesterday? Mass. Kilograms. What's the standard for distance? Meters from kinematics. And what is the unit for force? Of course, I mean, come on. I mean, they named it after the big guy himself. Although, by the way, just for interest, in England, in the United Kingdom, the unit of force is not Newton. In his own country, it's not Newton. I do. Okay, I'll say. Okay, I'll tell you why. There are two kinds. Listen up. there are two kinds of unit systems in the world, okay? Okay, metric and imperial. But there's also another system that also is neither one of them, but it depends more on the metric, but it's actually what? Instead of meters, it actually depends on centimeters. And instead of kilograms, it depends on just what? Grams. Yes. If you define a unit using centimeters and grams instead of what? Meters and kilograms, you do not get a Newton. You get basically what? A fraction of a Newton, okay? It's actually called the dyne. D-Y-N-E. And in England, they actually teach forces using what? Dynes. Mega dyne, micro dyne, kilo dyne, and so on. They actually don't use Newton, okay? Because England is still operating sometimes on what? Centimeters and grams instead of what? Meters and kilograms. If you want to do the regular official system international of units, you have to use what? Meters and kilograms, and only then your final answer will be in what? Okay. Which one here did I not bother giving you a unit of? The gravitational what? Constant. Okay. Do you think, okay, question for you. It's already a what? Do you really need the unit or do you just need the number then? Okay. Can you still, if you really want the unit, can you still work out the unit for it? Yes, you can. Let's think about this for a second. Remember unit analysis? Physicists and engineers and scientists, whenever they come up with an equation, what's the first thing they check? The units. Because if the unit doesn't make sense, I don't care how amazing the equation is. It is wrong. Like, let's say, for example, you came up with a unit to calculate, I don't know, the speed of a rocket, in a certain medium. And then you analyze the units, and the speed unit came out to be meters per second squared. Is that correct for speed? Go back to your equation. It is screwed up. Apparently, you're calculating for what? Acceleration instead of, do you see what I mean? You have to analyze the unit. So everyone, let's actually try to what? To play with the units and see what the unit of the gravitational constant is. Okay, just for fun, I guess. Okay, let's see. What is this one here? Okay. Do we know the unit for this one? So is it kind of like of an unknown? What do you call an unknown? There you go, x. Okay, okay. So what's my equation now? N equals x times what? Kilograms squared over meters squared. Go ahead. Tell me how to solve for x. Tell me how to solve for x. But by the way, is there one way or multiple ways? Multiple ways. What's a way I always like? Cross multiply. So what does that mean? Technically, those two are together, right? Are those two together? No, because there's a what? There's a 1. So let's actually what? Go and say n equals kg squared x over what? M squared. What crosses? What with what? X. Yep. So that makes kg squared x equals what? N m squared. And finally, what's x equal to? N times m squared divided by kilograms squared. And that would be the unit of the water gravitational. Did it really add anything to your understanding? No. But my point is what? Because it's a, have you ever, okay, question for you. Have you ever asked what's the unit of pi? You never do. You just ask what's the what? What's the number? What's the value of pi? Which is what? 3.14. By the way, what's the unit of pi? No. That's not the unit. That's a symbol. What's the unit? Nope. No. You're thinking way too much. Okay, I'll make it everyone. I'll make it I'll make it easy for you. Give me an equation with pi in it. Come on, go back to grade 10. Where do you use pi? You either use it for the what? The area of a circle or the what? This, no, not the not surface, no. Circumference. The perimeter. The only thing that doesn't have perimeter is the what? Is the circle. We don't call it perimeter, we call it what? Circumference. Can someone who remembers the equation for the circumference of a circle? You can do it in diameter or you can do it in radius. I don't like it in diameter. Who remembers it in radius? C equals what? Capital C equals 2 times what? Pi times. So let's solve for pi. Pi is equal to what? C over 2r. C is what? You just told me. C is what? The circumference. How can you measure the circumference? In what unit? Meters. How about r? What's r? Radius. Times 2, still what? Still meters. What do you get when you divide meters by meters? What happens to the units? They cancel out. Pi is a what? Is a unitless number. Do you see how? No. Do you see how you can always? But no. Do you see what I just did? I proved to you the method that you can always what? Follow to find the unit of anything you want. Put it back in the equation and replace everything with this unit. Do you see what I mean? And whatever cancels, whatever happens, happens. So remember, pi doesn't have what? Pi is a ratio of what? Of the circumference of a circle to the what? To the, what do you call double the radius? Yeah, by the way, isn't that what pi is? Pi, sketch any circle in the universe and then take a string, line it on the circle. That gives you what? That gives you the what? Circumference. And then take the string out and then what? Measure the what? The diameter. Divide the length of this string by the length of this string. You're always going to get what? You see what I mean? 3.14159 infinite number. That's the ratio of the full circumference to the full diameter. And ratios, but again, if I ask you right now, what's the unit of sine? No units, right? Because what's the definition of sine? Come on, Sokatoa. Come on. What's the definition of sine? Opposite over. No, opposite over. Opposite over hypotenuse. How do you measure the opposite in what? How do you measure the hypotenuse? What happens when you divide them both by each other? They cancel. That's why they call them what? Trigonometric what? Ratios. They're unitless. By the way, I guarantee you, go right now to first-year students and just stop them and ask them, hey, what's the unit of, okay, ask them, hey, what's the sine of 30 degrees? And they will tell you, or they can just plug it in, 0.5. Just ask them this, 0.5 what? Half of them will tell you, degrees. I just told you 30 degrees. So they're like, oh, okay, fine. Meters. You're like, no. They will give you every single possible unit they can think of. But they will never think of what? Dividing the units together and canceling it. Do you see what I mean? People sadly don't understand what they do. And yet they make it to first year. And it's sad because then you know what? You have no idea if your answer makes sense or not. Okay? All right. So important. You must use what here? Kilograms, meters to get what? If you do anything else, no. Question for you now. Do you think gravitation is really, really felt when you have small objects or big objects? Sorry, light object or heavy objects? Heavy. Again, you need something like Earth scale to what? To feel gravitation, right? Do you think the radius of the Earth is going to be measured in meters or kilometers? Do you see where people might make mistakes here now? Kilometers is more of a natural scale for the measurement. But is it the natural scale for this equation? So what do people end up doing? Forgetting to switch kilometers to what? To meters. How many meters in a kilometer? So how much are they off by? No, 1,000 squared. They're off by 1,000,000, right? Because remember, you're going to forget to convert. And then, because you forgot to convert, you're going to forget to what? Square it twice, right? So that's how I know that, for example, I will always know who forgot to convert kilometers to meter by looking at your answer. Your answer is correct, but your power of 10 is what? Is incorrect. I'm like, oh, their power of 10 is 6 times off. That's basically it. Okay? Again, it's out of experience. All right. So everyone, let's plug this in a what? In an example. So today we do case number 1. What's case number 1? So today we do case number 1, which is what? 2 small objects, and we're going to see the gravitation between them. How about the complete opposite of that case? Instead of 2 small objects, we have what? 2 big objects. Okay, how about the third case? Come on. 1 small, 1 big. That will be case number 3. So everyone, let's do this. And I love teaching this lesson because it's absolutely no physics anymore. It's just what? It's just math. Not just math. Punching in numbers. Boo to yourself. Okay? Go ahead. Calculate the magnitude of the gravitational force between you and the person sitting next to you, closest to you. Okay? Now, technically, everyone, what do we need? We need the mass of this person and the what? In what units? Kilograms. How many people here know their mass in kilos? Okay, how many people know it in pounds? Okay, how do you go from pounds to, if you have it in kilos, good. How do you go from pounds to kilos? What's the magic number? So 2.2, and yes, you divide, because the number in pounds is always what? Bigger than the number in kilos. Okay, what do you also still need? The what? Okay, now let's be honest. Technically, the distance has to be from where to where? From your what? From your center to your center, right? Makes sense, right? Now, obviously, you can bother measuring. You can say, Mr. Abna, can I borrow a mirror stick? And say, for example, you can say, okay, from Miriam Center to Yasmin Center, I'm going to say, again, it has to be in what? Meters. But oftentimes, you're not separated by a full meter. You're separated by what? Up to what? Centimeters. So you have to take that and divide it by what? How do you go from centimeters to meters? How many centimeters in a meter? Centi. What does centi mean? 100. Century. Cent. It always means 100, right? So we have to take that measurement and divide by what? By 100. So for example, from here to here, I'm kind of seeing like 65. So 65 centimeters, how much? But if you really want to take it easy on yourself, what do you just assume? You just assume you're off by how much? A full meter, right? Because then what's 1 squared? Which is 1 squared? 1, exactly. So if you want to make your life easy, yeah. So go ahead. Come on. I'm just going to leave it up to you. Come on, everyone. Go ahead. Plug in the numbers and show me whenever 2 people are done, raise your hand. Okay, everyone, pencils down. Watch how I'm going to do it in the least amount of math possible. Come on. So I'm going to use my mass, and I'm going to use Arabi's mass. Okay? So what's the equation as a generic equation? Fg, let me just hide this. Whoops, F capital G equals what? G times M1, M2 over D squared. Okay. What's the value of G? Standard, you do not guess it. You always have it. 6.67 times 10 to the negative 11. Okay. Now, Arabi, what's your mass? All right. Minus 62. All right. So 72, 62. Now, distance. I don't want to use 1. I don't want to use 0.5. I'm going to use 5. 5 what? 5 meters squared. All right. Okay. How many people forgot to square? Aha. You see? All right. No problem. No problem. No problem. No problem. Okay. What should I do first? Come on. What's the easy part of all this? Yeah, multiply. So 6.67 times 10 to the negative m. Okay. What's 72 times 62? Whatever that is. No, 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 no. I am showing you my way, which would make it easier if you actually think about it this way. Okay. Okay. So 464, 464 divided by what? Oh yeah. Yeah. Oh, I said it. Sorry, I wrote it. What's up? No, I squared it. That's all. Yes. Now, everyone, what should I do next? Yeah, thank you. Technically, there's a what under here? So I could what? I could level multiply, and then what? Or I could what? No, no, no. When do you only cross multiply? When you're trying to solve for an x, and there are what? How many fractions? Guys, come on. When do you only cross multiply? I don't want to ever hear cross multiply unless you're trying to what? Solve for a variable. Are we solving for a variable here? Or are we just trying to evaluate this complete side of the equation? Exactly. When you evaluate, you don't cross multiply. You just what? Level multiply. Okay? Again, when you cross multiply, when you solve for a what? An unknown, and there are what? If there's an equal sign with 2 fractions on both sides. Okay. How many people? Raise your hand. How many people would rather divide and then multiply? I'd rather do that. All right, let's divide. So what do we get? We get 6.67 times 10 to the negative 11. And this guy divided by 25. 178. Okay, fine. Point what? 56. Okay. I'll just, before I do this. So Uday, for example, raised his hand and he said he was done. But his answer was way too big. Why do you think his answer was way too big? Because he did all of this part, but forgot to multiply by what? Forgot to multiply by the gravitational, which means what? It did not go what? It did not go down as it should be. Okay. How do you multiply this? Everyone, Pencils down. Guys, eyes on the screen. This is how I would do it. Remember when I taught you about this button right here? This button right here? Where is it? What's this button? EXP. What does that mean? Scientific notation, exactly. Or basically what? Anything times a power of 10. So what's my scientific notation for the G? 6.67 times what? So I could just say, look, 6.67 x, and now it's waiting for the what? Just waiting for the exponent, for the power. What's my power? 11 with a what? Negative. So I have, mine has to do 11. Oh, sorry, 11, and then put negative. All right, times what now? Times 178. You see what it happens? It always converts it to what? In the middle, in the intermediate step, to what? To standard notation. But I don't have to do that. No, I don't have to do that. It does it. By the way, your calculator is not going to show you. Mine every time does it when it shows me when it does it. So but I put it in what? I put it in scientific notation. It just shows it to me as standard. No, I'm with you. But my calculator shows it to me as standard before I put the other number for whatever reason. You see what I mean? I put it as scientific. Look, I'm going to repeat again. I put it as scientific. But for whatever reason, it insists on what? Switching it to what? To standard. Times what? Times, what was number? 178.56. Okay, that's a bad notation. I need to make it what? Scientific. I can either plug in, not plug in. I can either press this button. What's this button? FE, or I can do the what? I can do the what? The hop, the jump. How many do I need to jump? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Let's see. You're right. It is 8. Okay. So what's the answer here? 1 point. 1 point. So again, yeah. Because, okay, everyone. Why is the power negative? Because the number started out what? Big or small? So it has to stay always what? Small. And a small number means what? Negative scientific notation. Okay. Everyone, what technically the sig fig situation here? It's 2 here, 2 here. What's better about this one? It's only 1. So let's make it what? No, let's make it 2. So now I have to keep everything to what? To 2. What would this one be? To 2 sig figs. 2 sig figs. It's already in scientific notation. Is it 1.1 or 1.2? It's 1.2 because you have to cut it here, and the 9 rounds this up to 2. So what's my answer? 1.2 times 10 to the negative 8 in what unit? It's a force. It's a force. Newton always measures forces. Thank you. What's up? Oh, here. Scientific, sorry, sig figs to 2. Yes. So, everyone. Okay, everyone, listen up. Okay, question for you. So Yasmin is asking, listen up. Yasmin is asking, is it just newtons? Okay, I have 2 explanations for you. Number 1, why is it just newtons? Because we're measuring what? We're measuring force. And we know from now on, force is always measured in what? Okay, what if she's still not convinced? What if she wants me to prove it? How can I prove it? I can plug in back all the units in, and I will get what? Newtons at the end. Do you see what I mean? I'll show it to you. Everyone, look. Yasmin, for example, is not convinced that this should be in what? Okay, no problem. Let's look at the units back. What was the unit? Everyone, what was the unit of this guy? The one we didn't need, but we worked it out anyway. Come on, what was it? No, that was the x. We solved it as an x. Do you remember what it was? I think oh crap, I deleted it. My bad. Do you remember what it was? I think it was, yeah, it was newtons meters squared over kilograms squared. So newtons meters squared over what? Okay, times. What about this one? Come on. Kilograms squared. Yes, thank you. Kilograms squared. And this one is what? Meters squared. Come on, tell me what's going to happen. Come on. Yes, Jenna, what's going to happen? Meter squared, gone with meter squared. Kilogram squared, gone with kilogram squared. Do you see what I mean? By the way, it's interesting. No, it's interesting. It's Newton because when we solved for the what? For the unit of G, we already knew this one is in what? Newton. Do you see what I mean? I already built this one to cancel the multiplication back into newtons if I ever have any doubt. Yes. But I didn't tell you. I wanted to show you that even if you forgot, I already built it from the system, imposing it to be newtons anyway. Does that make sense? So forces in any course you ever take is all measured in what? Forces. Is always measured in newtons, 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 and that's it. Nice. Okay. Now, question to everyone. Listen up. Question. Everyone, eyes on the screen. Guys, eyes on the screen. Does this answer make sense? Why is the force between me and Arabi is 1.2 times 10 to the negative 8 newtons only? Is that a big or a small answer? So does that make sense now why I don't gravitate towards him? Because this force is very what? Okay, here's a question for you. What if we are not here? Everyone, what if we are where Baha said, in a place where there is no other force effect? What would eventually happen if me and Arabi are at the same masses and 5 meters apart? Eventually, what's going to happen? By the way, am I going to be the only one moving, or is he also going to be moving? Okay, and question for you. As we move along, our mass is going to change. Masses. Our distance going to change. So as we move along, closer and closer, and we recalculate this, does this change? Does this change? No, this one. Does this change? Does this change? Does it become bigger or smaller? What happens to a fraction when the denominator gets smaller? The whole fraction gets what? Which means what? As we move closer, what's going to happen? Every single nanosecond to the force between us. Which means, are we going to keep going towards each other at the same speed or at a faster speed every single time? Exactly. Thank you. It's got to be what? Accelerating until we what? Smash. Why is this not happening here? Because how many other things are acting on me? First of all, gravity definitely is much bigger than what? Than the gravitation between us. What else? Also what? You said what? Friction. There's what? I'm probably trying to move, but what's happening? There's what? There's friction and stuff. Do you see what I mean? That's why you can never really discuss what? Actual physics whenever there are other things what? Masking the effects. That's why I like to go to what? Theoretical deep space. But does that make sense now? Okay. Okay. One last thing for today. The last thing is I like you to do a what? Sorry. Open your so in your notes. So student, I think today is 3 case 1. There we go. I want you to do a what? Everyone. A what? A reverse example. Now what do you have to do? You have to tell me the distance between you and your partner if the gravitational force between you is how much? 5.9 times 10 to the negative 9. Again, what masses are you going to use? The same 2 masses used for the first one. Come on, go. Go. By the way, everyone, before you do it, question. Is this one, listen up, is this one going to be plug and play or solving? Why? Because I'm trying to get what? Where is distance? Is it on the left side of the equation or the right side? Right side. So you're going to have to do what? Yep, go. Everyone, so now we know this number. Look, now we know this number. We know this number. We know this number. We know this number. I'm trying to find this guy. So technically, this is the one that's a constant, but now this one is known. Yeah. We're trying to find the d squared, and then we square root it. So I'm trying to find. Yes, d squared until. Thank you. Yes, it is my unknown until I figure it out. To the negative 10, or so to negative, is it negative 10 or negative 9? Negative 9, yeah. Yeah. That's my FG. That's my left side now. Yes. I know my out. Now I know my output. I need my input D. Everyone, I am seeing that people, listen up. People are still not plugging in the G. They're not plugging in the 6.67 times 10 to negative 11. I guess because you're using values for your mass and distance, you still don't realize that the G is known. You can just use it. Remember, the G and the M1 and the M2 are really on the same level. So you can triple multiply all of them together at once. Okay, everyone. So keep going. Okay, hold on. Keep going. And if you made a mistake, keep the mistake because I could go around and tell you exactly where the mistake. Let me show you what I'm going to do. Okay, everyone, question. How does this change now? Can you tell me how does this change? Come on, everyone, pencils down. How does this change? Do I still use 72 for Ari's math? Yes. 62 for my math. 6.67. Do I know this one? No. What do I call it? Yeah, like you called VF, for example, all the time until you solve it. So I'm going to call this one D squared. Don't forget the square, please. Okay, D squared. However, everyone, does this side now stay blank? What happens in it? I have to solve. Did you say so? I sub in. I have to plug in 5.9 times 10 to the. Okay. What should I do next? By the way, physics is done. Math takes over. How should I clean this up nicely? Ali, what would you do? Multiply times. Times what? Keep going. Exactly. You can imagine this to be extended all the way here, right? Great. Okay. So I'm going to do this. How many people rearrange the formula first? You did. Great. Let's see if you 100%. Remember, symbolic first, then numerical, or numerical first, then rearrangement. Same thing. Okay. So I'm going to keep the 5.9 here times 10 to the negative 9. But I'm going to put what under it? Come on. No. 1. I know I'm going to cross multiply, right? I know it's going to happen. Equals. Okay. What do I do with these three things? Multiply them. All right. And here is how you multiply all of them in one shot. Everyone look. Okay. 6.67. Do not do times 10 to the, you just do what? AXP. Thank you. X. What's my power? 11 with a what? Minus. Times. What's my first mass? 72. What's my second mass? 62. Boom. That's it. All right. Do you think I need to keep all of those decimals? I mean, what's my sig fig situation? Still what? Still, no, 2. So I'll keep 3 or 4. I'm going to keep 4. So I'm going to keep 2.977. Okay, everyone? So 2.977 times 10 to what power? 7. Yes, okay. 2 divided by. Now what do? Now I crisscross. Okay, so what's going to happen? What's going to happen is this. D squared times what? So 5.9 times 10 to the negative 9. D squared equals just what? 2.977 times 10 to the negative 7. Come on. What's my next step now? Everyone, what if this was just a D, not a D squared? What do you just do? You don't minus. You what? You divide. Like 5x equals 10. You divide one part by another. Okay. So D squared equals what? Equals what? Do you know how many people would make a mistake right after this one? You know why? No, no. If you plug this in into a everyone, if you plug this in into a calculator without using brackets, guess what's going to happen? It's going to multiply these two, and then what? Instead of multiplying these two first before dividing, no, it's going to multiply, divide, and then what? Multiply. That's why you don't use the what? The times 10 to just use the EXP, because the EXP tells it it's what? One block divided by what? Another block. Exactly. So look, I'm going to do what? 2.977. Oh, sorry. What's the XP what? 7 minus. That's it. You don't need to use brackets. It knows this whole thing is what? One what? One block, one chunk, one unit. Divided by what? Come on. Divided by? Come on. 5.9. Also EXP. What power? 9 negative. Okay. By the way, this is, see, that's why I hate stupid scientific notation. What's the plus 1? It's like times 10 to the 1. What's times 10 to the 1? 10. So you know what? I'm going to do it this way. Boom. 50.45. You see what I mean? Just multiply by 10. So I'm going to go with 50.46. So D squared is equal to what? 50.46. Is this my final answer? No, it's not. I need to what? I need to square it. So D is equal to what? The square root of 50.46, which is very close to the square root of what? 49. So it's 7 point what? 1. In what unit? It's a distance. You don't even need to work out the units. It's what? Meters. Thank you. One question though. What was the distance here? 7.1. Did any one of you in your first part get a force that was 10 to the negative 9? No, you got 10 to the negative what? An 8 or 7. What does it mean when a force goes lower? The distance goes what? Higher. What's the distance now? 7. What were the distances that you all used before? 1 point. So does that make sense now? If the force gets weaker, that means the objects are now what? Further apart, and vice versa. And that's today's lesson.